Hello there and welcome to the iRevise supplementary series for GCSE Physics. Our topic today is waves. We'll be splitting this up across two videos. Both videos will include questions on basic properties, electromagnetic spectrum, Snell's law, total internal reflection. This video will delve into the function of the eye in conjunction with lenses. As you see in the AQA, their paper 3 tends to be very heavy with lenses, function of eye, ray diagrams, all that sort of stuff. So that's what we'll be looking at also in this video. And then in part 2, we'll take a look at the seismic waves, which come from the WJEC, and analog digital signals, which we see in Edexcel. If these types of topics are of interest to you, then you can jump ahead to video number 2, but I would suggest that you stick around for the first couple bits here, because it's always good to see what different exam boards do for questions about total internal reflection, electromagnetic spectrum, that sort of thing. All right, and in that vein, I'd like to move on. This is a question from June 2019, paper 2 of the Edexcel, and it's just an excellent question because it shows the Doppler effect in action here. You've got a toy which is stationary, and we can see the sound waves are being emitted. When the actual object starts to move along, then we can see that it says here, draw an arrow to show the toy is moving, which direction. I'm not sure where they want us to draw. I suppose you can draw it underneath. Maybe you can draw it here. We'll just say that the center of the object is moving along. And you can see as a result, these wavelengths are bunching up in the front, they're spreading out in the back. In the back with B, this is where you'd have your red shift if we were talking about light, and if you're talking about light, then up in the front with A, you'd have a blue shift. Okay. Of course, with sound waves like this toy, I'm sure you're all familiar with the effect of a siren coming towards you and then driving away, or a very loud motorcycle or something. Most children can imitate this sort of sound in their play. It's very distinctive. You hear it a lot. Cars coming towards you and then driving away. And Doppler effect is used for sound effects in movies and that sort of thing. Right. Anyway, let's move on. Explain how the frequency of the waves at A is different to the frequency of the waves at B. Okay, so 4 marks. All right, well, let's go back up to the diagram. We see that they're more bunched up here. Okay, so we can say that the sound waves are more bunched up. Sound waves are bunched up. Please use full English sentences here. I'm just doing shorthand for time. If the sound waves are bunched up, that we know that means that the wavelength is smaller. Okay, or shorter, you could say. And let me draw the wave equation, by the way. So because we've got a constant speed of sound here, what that will mean is if these wavelengths are smaller, the frequency needs to be higher in order to maintain a constant velocity. So what that means is if our speed of sound is constant, and we know it is, then that means that the frequency is going to need to get higher as a result. Okay, so what you could say is at point A, it has a higher pitch. The sound is a higher pitch than at B. Don't say than B, then at point B. We're talking about the points here. All right, and I think this is pretty straightforward. We'll go, yeah, we've drawn the diagram, and here. So wavefronts are closer, therefore wavelengths smaller, same speed, frequencies larger, higher pitch. Okay, so pretty straightforward. Let's move on. All right, I've got a paper 2 from January 2016 here, and what's the relationship between frequency and pitch? I would say they are the same thing.
That's it? Yeah, that's it. Just like that, huh?
I have a very bad feeling about this.
I got a bad feeling about this.
I have a bad feeling about this.
Part B, what's the wave equation? Some exam boards give it to you, some don't. Edexcel needs you to know it. Calculate the wavelength. Okay, so if I want the wavelength, I'm going to rearrange, and my little frequency is going to go down underneath. And so they told us 340 divided by 160, and our wavelength is 2.125 meters. And in this question here, we've got a graph. It says draw a line of best fit. So get your ruler out and try to get through as many of these points as you can. Have I drawn a good line of best fit? I've got this one off the mark. I've got 1, 2, 3 above the line, and I've got 1 below. I try to have 2 on either side. Again, it's going to be much easier if you've got a ruler. I'm drawing on a tablet. I'm doing my best. That's not even a straight line. From the graph, find the speed when the temperature's, see, so I've not drawn the best line, but I'm going to say, let's say 340. I seem to think that's what it is anyway, from the graph. Don't draw your graph lines like this. It needs to be one smooth line. Don't double them up. Don't sketch them. But always have a ruler for your exam, please. And then the air temperature decreases while the foghorn continues to emit the sound waves. How would this decrease in temperature affect the wavelengths of the sound waves? Well, if the temperature goes down, air particles are going to move in closer to each other. The air will be more dense. And if the air is more dense, we know that sound travels faster in solids and liquids, but this air is not much more dense. That won't be the problem. But because the temperature's down, these particles are going to be less likely to move. And so actually, come on, let's think about it. We've seen it with the graph here. As the temperature goes down, so does the speed of sound. So if the speed of sound has gone down, and the frequency which this foghorn is operating is constant. All right, and then according to, of course, our wave equation, we know then that if the velocity has gone down and the frequency is constant, our wavelength will have decreased as well, something to that effect. Okay. Yeah, I didn't like that. I said, hey, it's the same.
Did that go the way you thought it was going to go? Nope.
And it was a very, let's face it, a very lazy answer here.
Oh, the ego on you.
For that arrogance, I shall see you dead.
They want you to explain the relationship. The relationship should be a key word, okay? Yes, I think, you can look at a question like this and take it for granted. What's the relationship? Look at what they're looking at here. They say the higher the frequency, the higher the pitch. That's the relationship, okay? Saying that they're the same thing is not the best. You could say they're proportional or something like that, okay? Right, there's the wave equation. We got that. Right, and so we got the right velocity there because we did 340 divided by 160. We plugged it in. We got the 2 marks. Here's the graph. These are the lines they will accept anywhere between these. They give you a bit of a leeway, so that's nice. You need a straight line within that indicated area. Pretty straightforward, 1 mark. The line of best fit is extended all the way to 20 degrees, and the student's own value from the graph, 1.5. So use the graph to find. Yeah, so whatever value you would have gotten off of the graph. So somewhere between 340 and 345. So I said 340, thinking that I meant 342. Yeah, it's 340. Well, they give you a range, so that's nice. Okay, and then what's going to happen when the temperature drops? Well, the speed of sound is going to decrease with temperature. We saw that frequency is constant, so the wavelength drops. Good. Okay. Paper 1 from June 2016. Let's see here which of these properties is the same for all waves. It is speed in free space. X-rays are imaging broken bones. Gamma rays are used for tracers, and microwaves used to heat food for patients. EM waves are transverse. Describe how the vibrations of a transverse wave relate to the direction of the wave it travels. Okay, so here's a transverse wave. We can say the particles vibrate perpendicular to the direction of propagation. That's basic transverse waves knowledge right there. Another wave used is ultrasound. Ultrasound make images of internal organs. Which of these could be a frequency for ultrasound? Well, it needs to be above 20,000 hertz, we saw. Okay. Scanner records the time, the depth. So you got to take half because it's got to go there and then reflect back. So it's double that distance. So we take it by a half. Yeah. Explain why the technician uses a half. Well, that's basically it. That's what we've said. The wave travels to the the interface between the two media, gets reflected, and goes back. So that is twice the distance, and we need to account for that basically. Something to that effect, something along those lines. Right, ultrasound travels faster in the patient than it does in the air. Explain how the change in speed affects the wavelength. Okay, well, you've got your wave equation. You can just say something along the lines, the source of the sound is constant. If it is traveling at a higher velocity, it will also have a larger wavelength. Right, so free space, yes, we said. We got these bits correct, that's fine. Perpendicular to the direction of the wave, that's right. I would say perpendicular. Ultrasound frequency is correct. The wave has to travel there and back. Any two of these. Wave travels there and back. Depth is half the total distance traveled. I like that. That's probably good. The time to the target is half the total time. With this equation, either you're taking half the time, okay, or you're finding the distance and then halving it because the depth is only half that total distance. Something along those lines, okay? And the wavelength is longer in the patient or shorter in the air. Why? Because of this, okay? And we said frequency does not change. So one of these two plus that it's going to be shorter. Some sort of reason. Number 7 from the same paper. We've got a block here. This looks like a typical practical. It's going to totally internally reflect. Notes about this. Okay, so the angle of incidence equals the angle of reflection. Yes, it does because it's reflected. Light speed changes when it's internally reflected. No, that's wrong. The ray entering the semicircular block is reflected. No, it's not. There's no reflection here because it enters at 90 degrees to the surface. That means the angle of incidence is 0, so there's no refraction. So, no. Oh. Every ray entering the semicircular glass block is reflected by total internal reflection. Well, that's not true either. The angle of incidence, if it's 0, does not deviate. Yeah, that's true. We just said that. That's what I said a moment ago. And the refractive index of glass is bigger. Yes, it is. That's why we've got TIR. Jewelers cut jewels so the total internal reflection is more likely. Light enters a jewel along AB and leaves along CD. Between B and C, there are 2 total internal reflections complete the path of the... Okay, so this... I'll do my best to draw a straight line. This will come here, and it's best to draw a little normal. It might be best to kind of work backwards. Have this one come down like this. There's going to be some symmetry, isn't there? Okay, I would imagine that you're going to come across here. It must be horizontal. I would imagine these heights need to be the same, but basically something along these lines. It probably helps if you draw a normal in there. We'll see what they say about for the 3 marks. Draw your arrows as well. Show by calculation that the critical angle for the refractive index of 1 point. Yeah, okay. Well, so inverse sine of 1 over 1.5, and I think that's fairly straightforward. Explain why the quantity called refractive index has no unit. Well, it's actually a ratio. It's a ratio of well, here it is. It's a ratio of the sines of these angles, and sines of angles have no units, and so it's unitless. This graph shows how the critical angle varies with refractive index. Okay, how can you tell the point 1.542 is not anomalous? Well, 1.5 is here, and it looks to me like this curve would probably continue along like that. So actually, I've got it right through 42 there. So you could just say extrapolate the curve, that kind of thing. Okay, suggest 2 reasons why these axes of the graph do not start from 0. Well, generally, refractive indices are 1 or larger. Okay, so we could say that we could say refractive indexes are 1 or larger, not below 1. They'll never be below 1. All right, and critical angles. You're not going to get critical angles close to 0 as well. Critical. I'm just writing that short for critical angle. They don't get that small. Don't approach 0. I would say something like that. That would be my guess. Let's have a look. Okay, so we had wrong, right. That's fine. I think we got that. That's good. Yeah, there's your diagram. So, like I say, I think it pays to draw in and then have this go back, and then it goes across. That's fine. Let's see, 1 mark for only 2 internal reflections, so there and there. The horizontal line here, and the ray does not deviate on exit. Well, that was already drawn for us, so I don't know what that means, but okay. Straightforward calculation. We did that, 3 marks. That's fine. That's why it's a ratio of the sine of these two angles. It's a ratio. It's a number. There is no sine is a ratio. It's a number. There's no the units in it cancel out. Whatever we said. Yeah. Plot. So we added the plot. Oh, yeah. So we skipped this bit before. Add the point to the graph. Well, yeah. It went right through because it extrapolated. So. All right, so you add that point, you got a mark. I missed it before. We got it now. It fits the pattern. It fits the trend. Extrapolation. There we go. Good. Okay. And then what was that thing about why does the graph not have 0? Reduced scale gives a fuller use of the grid. Yeah, it's always more than 1, the refractive index, and the critical angle is always going to be greater than 20. So that's what I said for these. I don't really agree with that first one, but that's what some exam boards will tell you. Some will say don't. So, but I like these bottom 2. That's probably better. Yeah, and you could say critical angle is never 0. Yeah, I like this. Reduced scale fits the data ranges. It's better for fitting the data. I mean, I do buy that, although I'm not a fan of this. I've got June 2016. This is an AQA paper 3. X-rays and ultrasound can both be used for scanning internal organs. Ultrasound is used to scan unborn babies, but X-rays are not. Explain why. Okay, very straightforward. You know that X-rays are ionizing radiation and can cause damage to cells, damage to tissue, lead to cancer, mutate cells, that sort of thing. So you can say that, and then you can say ultrasound is not ionizing. I think that's pretty straightforward for 3 marks. Let's move on. The behavior of ultrasound waves when it meets the boundary between 2 different materials is to produce an image. Okay, so how does this happen? Why? What's going on? Well, you know that when waves reach a boundary, if there's a difference in density of the material, and this could be optical density for light or just density in general for sound waves, you know there's going to be some of the wave going through and some of the wave being reflected. So when some of that wave is reflected back, we can time how long it takes, and it might travel through different material at different speeds, and the computer compiles this into a 3D image. Let's look at the mark scheme real quick. Yes, ultrasound's not ionizing, X-rays are, and they can they pose a risk. That's fine. Don't say they're dangerous. That's not good enough. You can talk about how it could, you know, do something to the cells, something like that. They get some different examples here. I think Edexcel is usually more about mutating the cell, altering the DNA, that kind of thing, causing cancer. But you can talk about impaired brain function, stunted growth, if you like. Okay. Right, and the behavior of the waves was we saw that they are partially reflected, and you see that you need to use that word reflected, don't you? And then the time taken to measured is also measured, and this is what gets the 3D image. You must be clear that not all the wave is reflected. All right. Moving on, we've got a question here about some pulses. And basically the equation will be velocity is distance over time. You're asked to calculate the speed of the pulse. You're going to subtract 30 from 80. You'll have 50 times 10 to the negative 6, and it'll be 4 centimeters. And that's your calculation. Okay. Part D, you've got an X-ray with a broken bone. Describe how X-rays are able to produce images of bones. Okay. Basically, an X-ray is just a negative of of what's been exposed, right? So if you've got X-rays going through the air or going through tissue, they hit the material behind, they hit the photographic film, and it gets exposed, whereas the bones block the gamma rays, nothing gets through there. It's a darkened image, and that you would just you see the inverse of this. That's basically what an X-ray is, okay? And X-rays are able to produce detailed images because their wavelength is very short, very small, all right? So moving on, yes, your speed for C should be 1600 meters per second. So it's like I said, you got to change your 4 centimeters into 0.04 meters, divide by that time, and you should get the correct result there. Okay. How are the images formed for an X-ray? Well, the X-rays are absorbed by the bone. They're transmitted by soft tissue, and these transmitted bits are detected on that film, something like that. Okay, remember that transmitted, I know you might think of transmitted as radio waves, but transmit just means that light is allowed through. If something is transparent, it transmits light. You can have material which lets different electromagnetic spectra through. When you transmit radio waves, they're going through the air. When we transmit X-rays, they're going through your tissue. So don't let that word throw you off. Okay, and yeah, we said short, except small, but I think short's probably preferable. Right, let's move on to question number 4 on the same paper. We've got here a diagram. Which of these correctly identifies the angle of incidence and angle of refraction? We're going to measure relative to the normal, so it looks like it's going to be an AD. Okay, I can't tick on here, so just have to remember what we've said. Here, glass is used to make optical fiber, has a refractive index of 1.5. Calculate the critical angle. It looks like they give you the formula here, but if you don't have it there in front of you, you know that the refractive index is the reciprocal of 1 over the critical angle. In other words, the critical angle is going to be the sine of the critical angle, that is a reciprocal of 1.5. So actually, I'll just scroll on and show you. So AD, we said 42 degrees. That'll be the sine of the critical angle is 1 over 1.5. So it's 1 over n. Okay, and then you just do your calculation and you get it. All right. Okay, moving on to C here, right? So you've got short pulses of light can carry information through fiber optics. Each pulse is made of lots of rays of light. In this particular case, you've got ray A and B, and they're going through this. Okay. You've got a pulse of light entering and you've got it leaving. Now they're asking you to compare down here. Consider the paths of rays A and B and explain why the pulse of light shown in figure A in figure 8 is changed. Okay, well, it's not as high, the intensity is not as great as it was, and it seems to me like the time for this pulse to pass through is kind of a little more blurred, it's a little more spread out. The reason would be is if you take a look at A and B, what's happening with B? B is traveling a much greater distance to get through this section of the fiber optic, and so it's going to take longer to go through, and that time's going to kind of draw it out, blur it out a bit. Let's take a look at the answer on that, okay? Ray B took longer than ray A, okay? Or you can say ray travels further, ray B travels further, you can say. Allow the rays emerge at different times. And so yeah, it's going to kind of blur things a little bit, but it spreads the pulse out. Okay, to answer this one, when they're talking about what's happening with these figures, you have to look at what's going on in figure 8, and you can say, hey, that time has been spread out. And why is that? Well, because ray B took longer, but the pulse spreads out. Okay, let's move on to number 7 of the same paper. There's quite a few lens and perception questions in the AQA syllabus. What's one cause of long sight? You could say something like the lenses aren't working properly, the eyeball's not completely round, weakened muscles controlling the flexibility of the lens, something along these lines. We'll look at the mark scheme in a moment. Long sight can be corrected by surgery. During surgery, the surgeon may need to cut and heat very delicate parts of the eye. What equipment is used to do this? It is a laser eye surgery. Okay, section 7b here. Right, so part B, a light bulb is placed between a convex lens and the principal focus, okay, and then it's moved to position M. Now, I can't draw this for you, but maybe I can show you in a diagram. Okay, so I'd like to introduce O Physics to you. This is a great website for different simulations and animations using GeoGebra. On this particular one, I'm going to have the object in between the lens and the focus like we talked about. We see that the image here is a virtual image. We see that it's upright. This is lovely. It tells you everything down here at the bottom. Okay. Now if we were to slowly move this object away from the lens and past the focus, you will see that at some point we will switch from virtual to real, and we will also see that instead of being upright, it is an inverted or upside down image. And we could also talk about distance from the lens as well, the image distance. But I think I think you can kind of see what happens there, right? So let me just, right, so here we are again. I'll try to keep the object height the same each time. We'll keep it at 2, let's say. Okay, so it's a virtual upright image. At some point we're going to go through the focus. There will be no image formed, but as we continue to move through, and you can see here that the image, I think the image is going to get smaller because it's no longer being magnified. So that's how I would describe what's going on there. I hope that makes sense to you. I think if you play around on these simulation sites or draw enough of your own diagrams when you're practicing, you should be able to do that. Let's see what we've got for the mark scheme here. Right, one cause of long sight, eyeballs too short, lens is too weak. You could say light is focused behind the retina. They're really big on these differences with the eyes. We can talk more about that later. Lens is unable to focus. Don't say it's old age or inherited. That's not going to work. You could say the cornea is not curved enough, something like that. We had said laser. What did we say about this image in moving away from between the lens and the focus to outside? We said the image would decrease. Yep. We said it would go from virtual to real, and it would go from upside down. It would go from upright to inverted. That's what we had said. Okay, so that's good. Let's move on here. Here's a diagram they want you to draw. Again, I can't draw on the AQA pages, so I hope you know how to do your ray diagrams for your lenses if you need to. I can just go to the mark scheme right away. So you draw your one ray through the center of the lens. Yes, you draw the other one through the focus. Oh, sorry. Here we're drawing from the object, so you go horizontal across to the lens and then through the focus on the opposite side, and then you get these dotted lines back, and there's your magnified upright virtual image. Okay, so you get 3 points. So you draw your line parallel to the axis through the focus. You get the other one going right through the center. You draw your image drawn here where your dotted lines meet up. That's your third mark. Okay, part D here. So this is a graph here of image distance to object distance, and they're telling you that when the object distance is at 4, the image distance for lens A is longer than for lens B. Okay, state why. It's 1 mark. Okay, so the image distance, so this means this object's further away. So I was having a look over here. All right, if we take a look at here, now to me, looks to me like if we've got a larger focus, we'll have a larger image distance. Now I should look at what kind of, this is a convex lens. Okay. Now I wonder if this means for when the object is in or outside as well. Because if we are inside the focus, we can see here to have a larger image distance. A larger image distance here would mean a shorter focal length, wouldn't it? There's the image distance larger. Okay, but if this object is on the outside of the focus, we see here that a larger image distance means a longer focal length. So I'm not sure what they're going for here, because the mark scheme's a bit tricky on this one. What would you say if the image distance is longer for A than for B? Well, they say lens A has a greater refractive index. That makes it a more powerful or stronger lens. And we know, I would hope you have learned, that the relationship, the greater the refractive index, the shorter the focal length. You can see that illustrated in this, on this page here. Okay, mammoth memory. Okay, here they've got a refractive index of 1.4, all things being equal, and there's a principal focal length here of 75 millimeters. They've got an increased refractive index, and the focal length has gone down. Okay, and there's probably a graph you could do of your sine theta versus refractive index, but so I think we're okay with saying the stronger the refractive index, the shorter the focal length. I'm all right with that. That's true. I'm wondering about, for this question, if you don't understand and see that. Okay, if I have here my object outside of the focal length, it seems that the shorter the focal length, the shorter the image distance. But if my object is inside of the focal length, then it seems that the image distance will increase when I have a shorter focal length, which is what we were saying. So I wonder about where these lenses are situated for this question, because it does seem a bit tricky. Okay, and then on to part 2. You've got a table now, and they want you to use the information in the graph above. And this table, we've got the object distance in centimeters. This is for between lens B and the principal focus. And you got the magnification. Right, so if we go up in 1 magnification, we go up by 5 in object distance. And if we go by 5 in object distance, from 0 to 5, looks like an image distance of 10 centimeters. If we go from 2 to 3, that's an object distance change from 5 to 6.7. So from 5 to 6.7, about there, that's about 30. What about if we were to go from magnification from 3 to 4? Then we've gone from 6.7 to 7.5. Now 6.7 is about at the 30. Oh, wait. 6.7 is not that far. 6.7 is about here, 20, isn't it? Ah, well, that makes more sense. We haven't gone up 30. We've gone up from 10 to 20. And now if we were to go from 6.7 to 7.5, 7.5 puts us up about 30. So we've gone from the 20 to the 30. If we go from 4 to 5, that's 7.5 to 8. So 7.5 is about at 30, and 8 is at 40. So it seems like for every rise in magnification by 1, we go up by 10 centimeters is what it seems. Part 3 here, we've got a convex lens, same type of glass as lens B, but has a shorter focal length. Okay, complete the figure to show how lens C is different than lens B. If it's got a shorter focal length, if you look at here, if I can change the focal length of this lens, if I make it a really short focal length, you can see the lens bulges out. Okay, and if I make it a very long focal length, we've got kind of a thin lens, don't we? So for here, if it's got a shorter focal length, it's going to be more of a bulge. Let's check our answers here. Diagram showing the surfaces of convex C having greater curvature, more of a bulge. There we go. Here, when magnification increases by 1, the image distance increases by 10. Good, 1 mark for that. Well, I guess 2 marks for that. You can read some of these other bits. I'll let you pause that. I'd like to move on. Let's go out to June 2017. This is also a paper 3. CT scans are used by doctors to create 3D images. Why are they at risk of cancer? Well, because we know that basically it's the same answer every time. You're going to say, hey, CTs use X-rays. X-rays are ionizing radiation. Ionizing radiation can cause mutations and can cause cancer. Although there's a risk, why do we carry them out? Well, we would only do anything that is risky is if it provides a greater benefit. Maybe we can find a tumor. Maybe we can find an abnormality. Maybe we can do something to help this patient. So the benefits outweigh the risk. Okay, child has a CT scan. Her mother stays in the room during the scan. One precaution: put her behind a lead shield, some sort of metal shield, some sort of something to kind of block her from getting exposed to any stray X-rays. Okay, ultrasound can be used to create 3-dimensional images. What's one advantage of using CT scans rather than ultrasound scans? If there's no change, if there's no difference in the density of the tissue, I'm wondering if those sound waves will reflect and give you a good scan. I'm wondering what they say on this one. Right, so we'd said for part AI, CT scans cause ionization because they use X-rays, something like that, so that's good. And that can cause problems, as we said. We said the benefits outweigh the risks. Good. Wear lead vest. Put them behind a screen. Check if the mother's pregnant or not. Yeah, wearing a lead vest, even sometimes the patient getting an X-ray on their arm or leg will be asked to put a vest on to cover up their torso and abdomen. Okay. CT scans give higher quality image. Oh yeah, that is true. They do. They do. Ultrasound scans. If you've ever, I remember when my daughter, we got the scan for my daughter. Very blurry. They're very hard to image. CT scans are much more detailed, aren't they? Okay. You can differentiate between different tissues of the CT scan. More resolution, clearer image. A view of a larger portion of the body. Yeah, the ultrasound is quite localized. A useful image more quickly. True. Yep. Quicker is not good enough. Accuracy and precision, not good enough. You need to say high resolution, more detail, clearer image. Okay. On to number 4 of the same paper. One type of digital camera uses both converging and diverging lens. What's the name of the light detector used in digital cameras? It's probably going to be a CCD. Converging and diverging lenses both produce images. What type of images can be produced? So converging lenses are convex lenses. It depends on where the image is. I will say both real and virtual. Okay. And with a diverging lens, I believe it is virtual only. Right, CCD is correct. Converging is both. Depends on the position. You can see quite easily here when if this lets me move outside here. So we've got real and virtual. Right, and diverging virtual only. Right, like we said. Okay, moving on. We've got a graph here. Each lens in the digital camera is made up of a different type of glass. Show the relationship between the frequency of light and the refractive index. Ooh, okay. Describe 3 differences between the refractive index of the glass used for converging compared to used for diverging. Well, the converging lens has a higher refractive index at all times. It's always higher than the diverging lens. Okay, what else could we say? I mean, we've got to get 3 marks. We're going to look really picky here. I believe that this solid line is a little more steeper. So its reaction to an increase in frequency of light means a slightly higher rate of change to get to a greater refractive index. That is a greater slope. And you could say that the peak, the maximum for the converging lens, occurs at a lower frequency. It's at about 750, whereas the peak for the diverging lens is maybe, I don't know, 780 or something. Let's see what they say here. Right, so refractive index of the converging is greater, yeah, for all frequencies. We said that. We said it increases more, yeah, because of that slope was a little bit greater. And it reaches a maximum at a lower frequency, yeah, okay. Just make sure that you are really explaining this well. Don't just say, oh, it's higher. You can say it's increasing at a faster rate or a quicker rate, something like that. Be detailed. Okay, at one frequency, the glass of the diverging lens has a refractive index of 1.6, and the angle of incidence is 20 degrees. Calculate the angle of refraction. Right, so this is a Snell's law equation, and you're going to just plug your values in. They had said that the angle of incidence, so this was, I believe, a sine 20, and we're going from air into the glass. And they were asking for this angle here, this sine theta. So I'll say sine theta is equal to sine 20 divided by 1.6. You'll get some number less than 1 divided by 1.6. You'll get an even smaller number. And when you do the inverse sine of that, you should get a number smaller than 20. So I get 0.21, and if I do the inverse sine, then I get roughly 12 degrees. All right, party. The focal length of a diverging lens is 40 centimeters. Calculate the power of the diverging lens. Give the unit. I don't have the equation sheet for the AQA, but I did look up Diopter is apparently 1,000 divided by the focal length in millimeters. So if we take this 400, and if I do 1,000 divided by 400, I get 2.5. So we'll guess 2.5 diopters. Okay, in part F, give two factors that affect the power of a lens. The refractive index is going to be one of them, and then of course the shape. Okay, and so with the lens we'll say curvature. Okay, let's look at the mark scheme. Answer to that rounds to 12. 2.5, yeah, okay, so the answer is negative 1 mark for plus 2.5 if you wrote that. 1 mark if you wrote 0.02 if you didn't do your unit correction. The unit is diopters. You got a mark. Oh, that's a 3 mark one. Oh, so you got a unit for, yeah, it says give the unit, so give it. The unit is diopters. Now, ask yourself, why is it a negative? Well, it's a diverging lens. So it's going to be negative 2.5. Right, so curvature, refractive index, you can say shape if you like, allow material, but let's come on, let's use some terminology here. Don't talk about density, talk about the refractive index. Okay, back to number 2, because I think I missed it before. Glasses can be used to correct defects in vision. Some are designed with lenses that can be adjusted to give different focal length. What's one advantage of that? Well, I mean, if you're, you can kind of be like your own optician at home. You can kind of just say, hey, notice I've started to need this a little bit more for reading, so you can adjust it yourself. Okay, don't need to buy new glasses. Okay, and then this is a written question here. Explain how the human eye forms an image. Your explanation should include how a normal eye causes light from objects at different distances to form an image, and why long and short-sightedness cause blurred images. Do not include diagrams in your answer. Well, I'm going to show you a diagram again from this O physics page. This is the anatomy of an eye. For normal vision, this distant object has a point, and we can see 3 rays coming in through the lens, and the point all meet there on the retina. Okay, so you could just explain that light from an object comes in, it is refracted by the cornea and the lens, and it forms an image on the retina. Let's use some of the terminology and body parts here. Okay. If somebody is, and this is if somebody is looking focused far on a far object. If they were to focus near on a near object, the same thing happens. Okay? So if you were to have something in front of you which is near, but you were to focus far away from it, whatever's in front of you, if you're looking far away, is going to be blurry. Okay? Conversely, if you're looking at something really, if they're looking at something really far away, but you're focused up something near, then that far object will be blurry. Okay. Now, how does it work with somebody who's nearsighted, such as myself? If I'm looking at something which is really far away, okay, and the object is far away, that point is not meeting on my retina. And this is what AQA seems to like you to say. You need to know that for a nearsighted or short-sighted person, the image is focusing before, or the image would appear before the retina. Okay, and you'll notice that for a nearsighted person looking at a near object, everything's normal, everything's fine. But what happens for a nearsighted person is the image forms before. Okay, now how do we correct nearsightedness? Well, you put in this diverging lens here. It's going to make things so that the image is formed correctly on the back of the retina. Okay. Right, if we were to talk about somebody who's far-sighted, that means they can see far away really well. If you've got an object that's far away and they're focused far away, you can see that point just goes on the retina nice. But they can't read up close. If something's really close, the image, you can see this point is going to form behind the retina. Okay, so it's the opposite of the nearsightedness. Now, how might we correct this? Well, again, put a lens in there which is going to converge, all right, and it's going to bring these, you can see it's going to bring these rays in a little bit tighter, and they'll be properly then therefore refracted by the lens, and we'll get that image there on the back. Okay, so that's kind of along the lines of what you would write about in here. Let's just take a look at the mark scheme. Okay, so yeah, they don't need replacing. You don't need an optician to prescribe these adjustable lenses. That's fine. You can pause and look at the rest. Let's move on to the mark scheme. Now, for 5 to 6 marks, you need to explain how an image is normally formed by the eye. which is what we talked about, and either explain how the lenses changes shape to focus the light in the different situations, okay, of being near or far.
Near and far.
Focused, looking at objects from far away and close up. We haven't quite done that, but we could explain and say, hey, look at the shape of the lens when I change from my focus from near to far. Look at the shape of the lens. If you're looking at something very far away, your lens is practically flat. If you're looking at something close, muscles in your eyes make that lens bulge out a bit more. That's the kind of thing you need to be discussing here when you talk about how your lens normally works. We were kind of looking at the other one here. Okay, so you either talk about the eye normally working, or you talk about how you correct for the long-sightedness with the image being focused behind, and you mentioned the short-sightedness is the image focused in front of the retina, and you identify those. Let's take a look. Let's move on down. So here's what you could have said. You could have talked about light enters through the pupil. Okay, so again, use this terminology. We didn't quite get there, but if you talk about enough detail here, light goes through the pupil. Well, I mean, the pupil technically is behind the cornea, but you got it. It's refracted at the cornea. It's going to be focused by the lens and the cornea. It should be focused on the retina. And we didn't mention this, but you can talk about how what happens is the image is inverted, real, and diminished, which means it's smaller in size. Okay, and then explain how light from objects at different distances work. Okay, so you could say, hey, when the object is different distances, we change the shape of the lens. These little ciliary muscles pull the suspensory ligaments, which change the shape of the lens. Distant objects, it becomes a less powerful and flatter lens. For nearby objects, it becomes a more powerful and rounder lens. Okay, or they say here fatter. Okay, you say that, or you talk about how you're going to get blurred vision if you've got short or nearsightedness, because what's going on in long sight, the image forms behind; in short sight, it forms in front of the retina. Okay, and you could talk about the eyeball being too long or too short for those respective cases. Okay, so that should be a fairly straightforward and fairly easy 6 marker, but maybe, bum around on the O Physics website, just have a feel for some of these, or some other, whatever demonstrations work for you so you can get a feel for that. Okay, and question 7 on this same paper. Again, it's about ultrasound, so we can kind of get through this fairly quickly. What's the minimum frequency for ultrasound wave? Well, it's going to be 20,000 hertz, I believe, is the limit of human hearing, so anything above that will be considered ultrasound. Okay, here, what do we have? Ultrasound is transmitted from the top of the wing, okay, and there's a small crack. The ultrasound can be used to detect how far the crack is from the surface of the ring. Is it on the surface or inside the wing? So the ultrasound signal on its own does not directly give the distance. Okay, what must be measured? Well, there'll be a reflection backwards, and then it will detect, because it's the detector up at the top as well. So we're going to measure the time it takes for the echo for the reflection, basically. Okay, because of that crack, there will be a part of it will be reflected back. We talked about earlier. What other information is needed to calculate the distance from the surface of the wing to the crack? The information we need is the speed of the sound wave at the ultrasound wave. What happens to the ultrasound pulse when it reaches the small crack? Well, there's going to be a reflection, because there'll be a change in medium, and because it's less dense, some will go through, some will reflect back. That would be my guess. Aircraft is safe to fly for at least 2,000 hours after a crack develops. And if it's tested every 500 hours of flying time, if a crack is found, the wings are replaced immediately. If there's a crack in the wing, an ultrasound test will detect the crack 99% of the time. Suggest why the interval between tests is less than the safe flying time after a crack develops. Well, I think we just want to be sure, right? If it's 99% of the time, we might not always catch it. So I think we're just being cautious. Right, okay. So they say 20,001 hertz. I would have just said above 20,000 hertz. They say except 20,000 hertz. I'll say above. That's a bit pedantic. Yeah, the time taken for the what was this? what measurement is taken. Yeah, well, yeah. So the measurement we said was the time taken for it to reflect back. Yeah. Okay. So we needed the speed of the sound wave. Describe what's happening. As we said. Okay. This seems to be common in the AQA. Some of it's reflected. Some of it's transmitted. There you go. Except it is reflected and transmitted. Yeah. Well, right. Okay. If a fault is missed on the inspection, it will be safe still. Yeah, it's just lower risk. We're just being cautious, is all. Okay, and then we've got June 2015 here. This is another paper 3. Ultrasound waves. We just saw minimum frequency 20,000 hertz. The wavelength of an X-ray is about the same diameter. Same size as the diameter of an atom. X-ray crystallography is a field in which you shoot X-rays at substances, and from this we can kind of determine the atomic structure. So atom is the answer there. Here, this one here is compare the medical uses of ultrasound and X-rays. Okay, you should talk about the risks, any precautions associated with ultrasounds and X-rays. Okay, very simply, ultrasounds we can see used here to look at babies in the womb. You can also use them to crush down kidney and gallbladder stones, and so that's useful. There's no precautions. The ultrasound's completely safe. That's about it. Okay, you can use it for imaging. The images, as we've seen, are not as clear, and it's a little bit hard to make things out. That's why you need to be specially trained on these machines. Whereas with X-rays allow you to take a look at holes in your teeth, cavities, looking at broken bones, fractures in your bones. Maybe if you ingest a certain isotope, you can look into your intestines, I believe, barium sulfate, something like that. But generally, we use it to look at bones. We can use them in the CT scanning we saw as well. And, of course, the precautions there would be you don't want to have too many X-rays in a certain amount of time. Even pilots need to limit the amount of hours in flight time because going up in an airplane exposes you to more X-rays than normally on the surface of the Earth. So limit the time, stand behind a shield, leave the room when operating, that sort of thing. And I think we've got it kind of covered. It would be along these lines. Go into more detail. We'll look at the mark scheme here. Okay, at least one medical use is given for both and linked to the risks and any precautions. That's what they want for 5 to 6, okay? So for X-rays, bone and dental stuff. Oh, yeah, killing cancer cells, right? We can use it for actually radiotherapy, okay? The irony here is that the danger of too much exposure is the ionization, damage to cells, causes mutations, increases the chance of mutations, increases the chance for cancer, abnormal growth, that kind of thing, okay? Now, of course, we want it to kill the cells. That's the whole idea of killing the cancer cells with X-rays, okay? There's a bunch of other things you can read here on the right. Pause that if you're interested about what's accepted and not. I'm going to move on. Operator precautions, go behind a screen, leave the room, that sort of stuff. Wear some lead-lined material in your, radiation badges. Oh, insufficient, okay? Because a badge only tells you how much you've been exposed to. It will not actually prevent the damage from being made, okay? Ultrasound, prenatal screening, imaging of body parts. You said kidney gallstones. It can remove plaque from teeth. Okay, that's a new one. I've seen these new devices you kind of put in your mouth and they do that. That's kind of cool. And I guess repair damaged muscle or tissue. Risks of ultrasound. Yeah, no risks, nothing. It's not, now don't just say there's no risks. I think you can go beyond. You could say, hey, it's not ionizing, doesn't damage cells. Precautions, you don't need to take any. So I think we did all right on that. You, of course, in these questions are going to want to craft your answer the best way because, as they say here, good English, organizing information clearly, using specialist terms where appropriate. You do want to make sure you practice that sort of thing. Let's go on. This is the same paper. Number 4, diagram of the human eye. You need to know all the parts. B, I believe, is going to be the retina. A looks to me like the ciliary muscles. Okay. What's the function of the iris? The iris is what controls the size of the pupil. It controls the amount of light entering your eye. That's the colored part of your eye. What's the name of the vision defect? Okay, we've seen this a few times. The image is being formed before the retina, so if memory serves me correctly, that is the short-sightedness. Looking at the mark scheme, suspensory ligament. Suspensory ligament. Oh. Okay, that's holding the lens. Ah, yep. But these are ligaments which hold the lens and change the shape of the lens. I think if we go to here, ciliary body. Okay, yeah, the ciliary muscles do pull the shape of the lens. If that's what AQA says it is, suspensory ligament, don't argue with your exam board. Go with what they tell you. I'm sure you would have learned that. Okay. Yeah, iris, control the amount of light entering the eye, the amount of light hitting the retina. That's fine. And we were right. Short-sightedness. You can say near. I think nearsighted sounds better. Short-sighted's more British, but short-sighted sounds like you've not thought things through. Okay. Or you can say myopia. Moving on. So this is just a lens diagram. They're going to want you to draw a ray diagram. I can't draw on here. I'll just go straight to the mark scheme and show how it should look. Okay, so you've got your object. You probably get construction lines. You're going to get a mark, a line parallel to the axis, and then it's going to dot back through the focal, and then a solid line going out, because this is going to be this is a concave lens. One line going straight through the center, and then it looks like they've got yes, you're going to draw. This is a tricky one. Normally you would draw a line in such a way and then dot it back through the other focal. This one's going dotted back through the image, and there's going to be this line going straight across. So you get any two of these construction lines, an upright image drawn where all of these dotted lines and everything meet. And there's your 3 marks. Okay, pause and read the rest there if you'd like to see that. That's fine. Part D, it's important the muscles can change the power of the lens of the eye. Why? Well, we can focus on objects far away and close up. It's really quite remarkable how that works if you really think about it. All right, and part E here. So the power range of an eye lens is the difference between the maximum and minimum lens power. Okay, you can see that even from the age of 10, it starts to diminish. Okay, this is measured in diopters. Okay, we can see here, calculate the maximum change that can happen to this is bold now, focal length of the eyes of a 60-year-old person. Okay, well, we'll use the graph here. 60-year-old gives us 2 diopters. Okay, now you need to remember a diopter is basically a reciprocal meter. They want to know what can happen to the change in focal length. So I think if we've read 2 off of the graph here, I think we're going to do a reciprocal of 2, and a reciprocal of 2 diopters would be 1/2 a meter. So half a meter. Right, so part D, we said so we can see objects clearly at different distances, so we can focus the light from different objects. And there we go, half a meter. The unit is not an independent mark. An answer 0.5 without a unit, or with an incorrect unit, gives you 1. A substitution of 2 equals 1 over f. Scores 1 mark. Yeah, okay. So there we go. That's not bad. Part I of E here. Compare the change in the power range of an eye between the ages of 10 and 30, between 50 and 70. So between 10 and 30, it's pretty smooth. It's pretty constant. I don't know if they're asking you for a calculation. I'm sure you can calculate the gradient here. You could say from 50 to 70, it's actually got a stronger slope, doesn't it? It actually is a much further drop, and it starts to kind of level off a little bit here at 70. So what would I want to say here? I'd say between ages of 10 and 30, it's a straight, constant, gradual slope. Maybe do a calculation if you like. You could say between 50 and 60, it's a much larger jump, but it does tend to be decreasing at a decreasing rate because it seems to level up a little bit at 70. Okay, and the last bit, use the figure 9 to show the power range of the eye's lens for a 90-year-old person. Okay, well, because this is kind of starting to level off there, and we're getting pretty close to 0 in diopters, we know we can't have an inverse of 0 for a focal length, like infinite focal length. Okay, so I'm imagining we're going to have to level off somewhere. I'm going to suggest maybe about 1. And the reciprocal of 1 is 1, you know, is that kind of thing? That would be my guess. Okay, so 10 to 30 decreases linearly or at a constant rate. That's what we said. If you wanted to calculate the gradient, you could. We said 50 to 70. It falls less rapidly. Falls less rapidly after 60. Okay, so to me it's sharper, but at about 60, that's where it levels off. We said. So it's less rapidly after 60, but it is quite a faster drop, I would say. It decreases at a decreasing rate, we said. Good. If you want to calculate some slope, that's fine. And we could say that this is what we had said. The decrease from 10 to 30 is less than 50 to 70. The gradient here is greater from 50 to 70. So, yeah, we got the 3 marks for that. That's fine. Now, this last bit, 0.8 diopters. Accept answers in the range of 0.6 to 1 diopters. Okay, so that's about what we said. I think we'd said it was going to level off here. I think I'd said to about 1. Maybe from this gradient you can go a little bit below 1, and they say 0.8 or anywhere between 0.6 to 1 diopter. So that's not bad. Okay, and I've got a January 2013 specimen paper here from OCR. Real quick question. We've got a diagram of some waves. Use the information to find the wavelength of the waves and calculate the speed of the surfer. Okay, well, the wavelength to me looks like 2 wavelengths for 40. So the wavelength is 20 meters. And the frequency they tell you is a quarter. So 0.25 times 20 is going to give us a wave speed here of 5 meters per second. I don't have a mark scheme, so we'll move on. Okay, I've got a June 2016. This is a paper 2 for Edexcel. We've got a student here who's vibrating air across a plastic pipe to monitor the sound. Let's see. Explain the meaning of pitch.
Oh, déjà vu.
Well, I would say that pitch is the same thing as frequency, and you want to explain what frequency means. You could say it's the number of wavelengths per second, but I think to be more exact about the pitch of the sound, you could say how low or high the note sounds when you play the note. Okay, I'd explain it as the high pitch is the high end of the piano, and the low pitch is the low end, the left end of the piano. You could think of it like that, maybe. They're going to do an experiment. They're going to measure the length of the pipe and the frequency of the microphone signal. 2 instruments they would need. Well, one of them is going to be a ruler. Is there a way you can measure the frequency of something? I think I know, because I've seen this in mark schemes before. A guitar tuner, piano tuner, maybe. I mean, you can get an app on your phone. I don't know if they'll take that nowadays, but I know I've seen students with phone apps adjusting for different frequencies. Maybe an oscilloscope. Maybe that'll go. Name the dependent and independent variables. Well, what were they doing? They were doing an experiment. They had 2 different lengths of pipe. So I would say that's the independent variable, length of pipe, and then the frequency was going to be the dependent variable, wasn't it? And this is the data that they collect. It's just 3 ways to improve this investigation. I would say the greater range of data. There's not much of a difference between 1.5 and 2 meters. You probably want to go, let's see, greater range for data. We probably want to have more intervals of data. And you probably want to take a number of trials and do an average. Number of trials and do an average for the frequencies that you measure is what I would say. Okay, so pitch is frequency, yes, and whether the note sounds high or low, that's what I had said, yeah.
I'm a quick learner.
You know, Lloyd, just when I think you couldn't possibly be any dumber, you go and do something like this. And totally redeem yourself!
You can say high sound is high frequency, something like that. Okay. Yeah, don't talk about other wave stuff. This is a perception of sound type question. Okay. vibrates more often in a shorter amount. Oh, okay, so you could say the higher the frequency, the more vibrations. Okay, that's fine. We said a ruler. Okay, yeah, there we... Oh, mobile phone app. There, it's updated 2016 already. Okay, yeah, and you can do a guitar tuner or something like that. That's fine. Okay, good. There we go. Dependent was frequency. Length was independent, we said. And repeat and average the readings, we said. Larger range. Good. Some intermediate values. Is that... More intervals. Yeah, I mean, look, I'm just talking out loud here. I would hope you'd write in a little more detail. What does more intervals mean? What I mean to say was, I wasn't very clear on that with it, let's be honest. More interdivisional steps there between the highest and the lowest. That's what I mean by that. So they've said intermediate values. That's probably better. Okay. Yeah, improved precision from the measuring devices. Yeah. Okay. Add in a control variable. Temperature. Yeah. Okay. Plot a graph of frequency and length. Deal with anomalies. Yeah. Because all they really did was have this table here. So is there an anomaly there? We don't know. That's why you do a number of trials. So I think we did fine for that 3. Plenty of things you can say. When you get a question like this, you really got to say, okay, yeah, I can do this. And if you've done just a handful of experiments in class, hopefully that'll come to you. Okay? You can pause there and see what else they've written there for C. But I think we should move on. So, yeah, this is 2015. This is a June paper 2 at Edexcel. Real quick, what's the type of radiation for cooking? Interesting. I could say infrared or microwave. Probably they're going to go microwave for some reason. Treating cancer. I've seen in a previous question about X-rays treating cancer, but I'm pretty sure we say gamma. And identifying broken bones, yeah, see, there we go, X-ray. Part B, all types of electromagnetic radiation are emitted at the same speed. Okay. William Herschel, he investigated infrared radiation, and I guess he passed the electromagnetic radiation through a prism. It refracted the radiations by different amounts. Here are the paths. Add where the infrared ray would be. Well, the infrared would probably be like this. Okay, probably. I want to draw this a little bit better. I want it to move towards the normal, and up here away from the normal, but it should kind of spread out a little bit. I would say this is IR. We'll label it. It's right about where red would be. Herschel used a thermometer to detect infrared radiation. He colored it to make it more effective. It would be black because it would absorb the heat. Let's take a look at the solutions. Yeah, cooking for micro or infrared. Okay, good. That's good to know. Either one they're happy with. That's fine. Yeah. Oh, and so treating cancer, ultraviolet or X-rays or gamma rays. Okay, very nice. Broken bones, X-rays. Same speed. Yes, we said. Draw the ray shows refraction to the correct direction at both surfaces. It's drawn above the yellow and it diverges from it. That's what I was trying to show you. Here we don't want it parallel to, it needs to be kind of moving away. Okay, and then also this multiple choice here was black, so that's fine. And here we have a Physics A Gateway Science paper from OCR. This is from June 2018, a paper 4. We've got a teacher here using a ripple tank. The frequency of the water waves is 0.5 hertz. What's the number of waves produced per second? Well, if we've got half a wave per second, times 5 seconds, then that's going to be 2.5 waves in 5 seconds. We increase the frequency. What's going to happen to the speed and the wavelength of the water waves? Okay, well, this question, we are in no way changing the depth of the water. Therefore, the speed of the wave should be constant. And that means that if we are increasing the frequency with that little vibrator, then that means we're going to have to decrease the wavelength. And you'll see that if you've seen the ripple tank in class, that when you vibrate faster, you can see that the wavelengths do get closer together, don't they? Okay, student tries to describe water waves in the sea. Water waves move up and down. The water particles move all the way across the surface of the sea. This means that the water moves in the direction of the waves. Part of his explanation is incorrect. It is this middle sentence, isn't it? Okay. We don't have water from North America going all the way across the Atlantic Ocean and hitting on the shores of Europe or Africa. We don't have that happening. It's blatantly untrue. So what we want to say is these water particles move perpendicular to the direction of the water waves. Okay, the particles do not propagate, only the energy propagates. The energy moves in the direction of the waves. The particles move perpendicular to the direction of the waves. For 2 marks, something to that effect. Right, and actually there's a question like this also in part 2, but we'll take a look at this one here in part 1, so it's a good mix. We got a student watching a ball game. He sees when the ball's hit, but he hears the sound a short time after. That's because the speed of light's greater than the speed of sound. Describe an experiment. Okay, well, let's keep it in the baseball context here. All right, so describe some measurements, calculations, and procedures to gather accurate and reliable results. All right, so let's set it up this way: that we will before the game measure the distance, let's say between home plate and wherever you are safely in the stands. Okay. And I'll just say, measuring point for now, but where we are in the stands, okay, you've measured that distance ahead of time. We're going to use the equation distance divided by time. Okay, so that distance that we've measured will be plugged in there. We will calculate the velocity a certain way. We need to measure what the time is. Okay, and so you can talk about how we will record the time delay between the visual, okay, between the bat striking the ball and the crack of the bat. What we should do is we should average, 3 to 5 trials. Okay. And the beauty of this is that we can do this for every at bat because maybe we use a video or a computer to record this. Maybe you sit in the stands and just have a stopwatch, okay? But they want you to talk about the measurement. They want you to talk about the equipment. You could talk about, I'm using a computer, I'm using a stopwatch, whatever to make these time measurements. You're going to average them, and once you've got your average time, you're going to divide your average time into there, and then you should be able to get a good value for the speed of sound. Something along those lines. We'll take a look at the mark scheme in a moment. Okay, and then this last part here. So we talked about function of the eye. We'll talk about function of the ear here. I guess there's a few more of these in OCR. So this is a nice little setup of the outer, middle, and inner ear. Sound waves outside the ear transfer energy to small hairs, cilia on the inside. The cochlea sends these nerve impulses into the brain. Explain how the sound wave disturbances in the air outside. Okay, well, this is the basic function of the ear. And so what happens is sound waves will hit the eardrum, which is, you can say, is a membrane. It's going to vibrate, okay? And then what happens is there's a small little bone called the hammer. It's got a little surface that is up against the membrane, the eardrum. And what happens is the way these three bones work together, the ossicles, okay, the smallest bones in the human body, the hammer, the anvil, and the stirrup, they work together as some sort of amplification, all right? And what that causes is vibrations in the cochlea, okay? And then the cochlea, as they've told us, have little hairs inside. Inside, we've also got a fluid, okay? And then here's, by the way, these little vestibular bits, and there's fluid in those, and when they slosh around, that lets you know, you can see how there's 3 axes these things are oriented, and that gives you your sense of balance, okay? But you've also got fluid in the cochlea, and that kind of is going to send the vibrations or the little wave impulses through for the sound, and it's going to cause the little hairs to vibrate. The hairs are connected to little nerve fibers, which then send the signal into the brain. It's only 3 marks. Yeah, let's see how we've done there. Okay, so 2.5 we had said. The speed is unchanged. The wavelength is reduced. Notice how those words are bold-faced. They must include an idea of speed, must include an idea of wavelength. Okay, so answers that merely state no change and reduces. No. You have to say which is matched up with which. Use your terminology. Okay, and then this part's about the water waves. The water particles move up and down. They move 90 degrees perpendicular to the direction of the travel. Okay, so that's what we had said, and then energy moves in the direction. All right, now any 2 of those points, which I think we got. Okay, you can pause on the right here to look at the bits that they ignore or allow for. Let's move on, though. And then, yeah, so this experiment, how would this work here? Okay, so we're going to produce some sound. Action to produce sound and seen by observer. Yeah, so I just like the baseball, but I mean, you could describe any other experiment. You could clap 2 pieces of wood together. Yeah, you could have a starter's pistol. We'll talk about this in the other video as well. These are good questions to make sure you've mastered. Allow, draw a diagram. That's fine. Using standing waves. Oh, interesting. That's interesting. Okay, yeah, you could do it that way as well. Right, measure appropriate distance. Yeah, so we talked about doing that before. Talked about measuring devices. Yeah, it'll be a speaker and a microphone, that sort of thing. Or, just from the home plate. We don't need a speaker in that case, I guess, if it's the baseball. Measure the time. Okay. And hearing sound, or, we're measuring something. Okay. There's the formula we're going to use. Okay, that's the formula we're going to use. Hey, look it. There's another way you could do this here, frequency and wavelength. So if you know what a certain frequency was, because you got one of those little pitch things, you get somebody who knows, oh, middle C is 256 hertz, that kind of thing. And if you were to measure the time it gets, you can calculate the wavelength. Yeah, it's a bit more advanced. You could do it that way as well. And then the idea of repeating the experiment, taking an average of so repeating and taking an average. So different trials and then averaging them, you got a mark for that. So I think from what we said, we probably got our 5. You are going to want to practice these answers several times to make sure you've got all the points, okay? And practice describing different experiments, different scenarios. Work out for yourself which is the best way you can describe this experiment, okay? And as we see, OCR, WJEC, Edexcel, they like to ask these questions. Okay, then finally on the working of the ear here. The outer pinnae. I missed this bit. Yeah, it transfers the sound waves. The outer pinnae. This is a characteristic of mammals. Mammal ears. All mammals have this. An external part of ear. It's cartilage based. Some animals can move them, but they act as a funnel of getting the sound waves down into the eardrum. So I might have missed that bit. Okay, it did say outside the ear to inside. So I got going right away with middle ear. That is a key bit for the outside of the ear. Mentioned the pinna, or plural with the E at the end, pinnae. Okay, the eardrum vibrates. It causes these bones to vibrate. They amplify the vibration, as I said. Liquid inside the cochlea transmits to small hairs, and these little small hairs will kind of vibrate. You can think of like an ocean current with the little seaweed at the bottom of the ocean floor kind of swaying with the vibrations and the waves. And then we said the small hairs vibrate. So any 3 from, okay, so I missed the outer pinnae, but that's fine. We still got it. This is outer ear. This is inner ear. This is outer ear. This is middle ear, and then down here is the inner ear. And if you want to do one of each for the 3 bits, that's fine. But I think even just saying what's happening in there, eardrum vibrates, causes the bones to vibrate, which causes an amplification. I mean, that's good enough. Okay, but yeah, quite a nice little question. Okay, and that takes us up to about an hour. Just to recap what we've done here, we've been looking at lenses and function of eye. This has been mostly from AQA. We will continue in the next video, part 2, looking at wave properties, Snell's law, total internal reflection, electromagnetic wave uses. We will be looking at all of those. Plus, we'll go on and take a look at seismic waves and the analog digital signals. Those are from the WJEC and Edexcel respectively. Thanks for watching, and we'll see you in the next video.